Alright everyone, we're going to focus on nuclear decay equations. So we know that there are atoms that have to kind of change their nucleus so they become more stable. And we're going to look at those kind of equations and how they do that and the different types of decay they can go through. So this video lesson focuses really on content standard AS3, using those nuclear equations to determine the type of nuclear decay an atom is undergoing. So let's get started. So a quick definition, and just kind of reiterating something we've talked about. The radioactivity is just the spontaneous emission of matter or energy from the unstable nucleus of an atom. So we have an isotope, it's unstable, it's going to start getting rid of stuff, getting rid of particles, whether it's protons, neutrons, positrons, to become more stable, in an effort to become more stable. So there are three types of radioactive emissions that we focus on. The first being alpha emissions here, and then beta emissions, and then also gamma emissions. Now you see this arrow down here at the bottom. That is showing the increasing penetration ability of the three types of emissions. So alpha emissions pose really no threat to us. They are very weak as far as penetrability is concerned, so they can be kind of stopped with a sheet of paper. Beta emissions, a little stronger, but still don't pose a big threat to us. Large sheets of plastic would be able to kind of protect us from any of the beta emissions we would come into contact with. The biggest threat for us are gamma emissions. The main reason is because they are so much stronger than the other two, and they're not really particles that are being released from the nucleus. It's really just like beams of almost energy that are being released, which have high penetrability powers. So gamma rays, kind of things we've used them for, and why, for treatment of cancer. Along with chemotherapy and other things, they'll use radiation. This is what that's referred to as, to kind of kill cancer cells. But then also there are other uses where engineers, because they're able to penetrate better than X-rays, engineers sometimes use them to look for cracks in pipes and aircraft parts, since they can penetrate deeper than like a normal X-ray when you're able to see inside of those. So just the three that we're going to focus on. Now, one thing is, before we kind of get into the actual equations and things we're going to look at, just some of the basics of a nuclear equation. It might look a little different than what you're used to. So we'll start with the original isotope. Whatever that will be determined kind of as we start talking. So the X just marks what that symbol for that isotope would be. We would put its atomic mass here and its atomic number down here. Now we move over to the right. We have our arrow. So we start with our original isotope. We'll be creating a new isotope here. So same thing, atomic mass, atomic number. We'll have the symbol for the new isotope here. And then the three types of equations we're going to look at. Well, the particle that's kicked out of the atom will kind of fill in this blank here. So you have three things that are kind of part of your nuclear equation: the original isotope, the new isotope, and the particle that was kicked out of the atom when we're looking at those things. Now, if you could go ahead and pause the video and go answer questions 1 and 2 down below the video, and once you've answered those, come back up to the top of the page and continue watching the video. So the first type of emission we're going to talk about is an alpha emission. So bringing this here, you can see that we have the nucleus of an atom here, and then an alpha particle has been kicked out. Now this alpha particle contains 2 protons and 2 neutrons, and to look at that a little closer, we'll bring up an actual example here. So we have the original isotope here. We have uranium 238 using the atomic mass. So the decay of it happens, right? It needs to become more stable for one reason or another. So it kicks out an alpha particle, which now you can see here, 2 protons, 2 neutrons. That's going to give us a helium atom here. So an alpha particle really is just a helium atom. That's a main point we need to make here. So then because of that, we kick those 2 protons and 2 neutrons out. We're left now with our new isotope, or what's referred to here as our daughter nucleus, is thorium-234. So we took 2 protons away, right? So that gives us 90, which means it's thorium. And we then took 2 protons, 2 neutrons, that total a mass of 4. So we're left with 244. So thorium-234. Now, to look at the equation for that, and what that would look like, so we would just kind of take those symbols. We have uranium 238 here with 92 protons, so it's uranium. The decay happens, so we've taken our helium atom away, we've kicked that out, our alpha particle, which leaves us with thorium, and we are left with thorium-234 as our atomic mass as well. So if you add these two up, you should get 92. You add these two up, you get 238. That only applies to an alpha emission, where you could add up this side to make sure that you have this side. Now, to look at a closer example, so we have gold 180 that is going to undergo alpha decay. So gold, if we have a periodic table, oops, I need to be able to write, sorry. We have gold 180, that's my atomic mass. Gold has an atomic number of 79, so we have gold 79. It's going to undergo an alpha decay. So I know because it's an alpha decay, I have to kick out a helium atom. So I'm going to get rid of a helium atom. And again, we talked about we could add these up or subtract them in this case to figure out what our new isotope is going to be. So 79 minus 2 would be 77 for my new atomic number, and 176 for my atomic mass, because 4 plus 176 would be 180. And since I now have 77 for my atomic number, I now have iridium as my new isotope, because iridium's atomic number is 77. So that's how we pull that symbol out through there. So again, starting with the gold, I need to kick out a helium atom because it's an alpha decay, and then I'm left with a new isotope, which is iridium-176. Now go ahead and pause the video here and go answer questions 3 and 4 and come back to the video. So the next type of emission or decay that we're going to look at is a beta decay. Now there's some things that we have to really focus on here so that we understand the equation that we're going to create. So here we look at the beta emission, we look at the image, we have our nucleus, protons, neutrons. We can see that an electron is kind of getting kicked out of the atom. So an electron, now there's more to it than that. It's not just simply an electron is being kicked out. What's really happening is, first, right here if we look, a neutron is broken down into a proton, an electron, and an antineutrino. We are not really worried about the antineutrino. That is like much deeper into chemistry and even physics than we would ever go. But just know that those are the three things that get kicked out. A proton, an electron, and an antineutrino. Now, the electron is what is kicked out of the atom. So the electron, and actually the antineutrino is as well, but we're only focused on the electron. The electron gets kicked out of the atom, and then the proton that was created, created from the neutron, it gets absorbed into the nucleus. So therefore, that's going to change our element. Now, looking at that in a very specific example, I know these numbers might be hard to see, but we have cesium-137 here to start. So we have cesium-137. So here, there's a simpler picture here. The neutron becoming the proton and an electron. Electron is kicked out, and that proton is absorbed into the nucleus. So the proton is absorbed into the nucleus. Now, the equation for this, would look something like this. So where we would have cesium-137, right, with our atomic number 55. The decay happens, so we kick out this electron over here. So this is why I said we can't really just add all of these. You kind of could, but just understanding what's really happening, if you just add them up, won't do anything for you. So our atomic mass doesn't change because what we did, we took a neutron and just kind of replaced it with a proton. So that doesn't give us a gain of anything for our atomic mass. However, we gained a proton, so therefore the element is now barium, because we went from atomic number 55 to an atomic number of 56. And we have the electron here, or the beta particle is what we could refer to it as, because it kicked out one electron, so it has a charge of -1. Now, you look, these add up. These do kind of add up together. These two add up together. So you could be able to check your work that way. But really understanding that this is an electron, and the proton came because the neutron was split up into two individual particles. So we're going to look at a beta emission example where terbium-189 undergoes beta emission. So we start with the atomic mass, which is 189, terbium, which is Yb for the symbol. It has an atomic number of 70. So again, we undergo the beta decay. So beta, meaning we're going to kick out an electron, beta decay here. So where we have an electron, -1 charge. Now remember, with beta decay, we increase the number of protons in the nucleus. So therefore, by 1, because we split a neutron. So we add 1 to the atomic number. The atomic mass will stay the same, which then 71 will give us lutetium, which is Lu for the symbol, because its atomic number is 71. So remember, we're going to add 1 for a beta decay. We're going to add 1 to the atomic number because we split a neutron, and this atomic mass will be the same because there was no actual change in the number of protons and neutrons. We just kind of converted one to the other, and we kicked out a neutron, or an electron, sorry, in the process. So go ahead and go answer questions 5 through 7, and then we will look at the last type of decay. Alright, so the last type we're going to look at is a positron emission. Positron emission is very similar to beta decay. It is actually sometimes referred to as beta plus decay for a couple reasons that we'll look at. Now, first off, again, looking at the nucleus, we have our nucleus here, protons and neutrons, and we can see that a beta plus particle, or a positron, they are the same thing, is kicked out of the nucleus. Now, where that comes from, what's happening kind of inside the nucleus is a proton, so one proton, becomes a neutron and a beta plus particle. So we take a proton and break it down into its simplest form, which breaks into a neutron and a beta plus particle. Now the neutron again stays in the nucleus, so the neutron will stay here, but the beta plus particle is what gets kind of kicked out that we've talked about before. Now to look at a more like an actual example of that, again these numbers are a little kind of grainy, but what we have here, we have a sodium ion. Actually, we have a sodium 22. It undergoes beta plus or positron decay. So we see here again, the proton becomes a neutron and a positron, or beta. That's another symbol for positron, or beta plus, which then the neutron comes into the nucleus and the beta plus particle gets kicked out. Now, if we look at that as the equation goes, as far as the equation goes, we can see that we have sodium 22 here. It undergoes decay. Now we can, if you look at this, we see that in this case the atomic number decreases because remember we took a proton and it's no longer a proton anymore, it's a neutron and a positron, so that decreases our atomic number by 1. So it decreases the atomic number by 1, giving us a neon in this case because 10. The atomic mass doesn't change, right, because we just kind of swap protons and neutrons, so that won't change our atomic number at all, or sorry, atomic mass. And then we kicked out a positron, so a positron in our case is going to be written with a 0 for the atomic mass, because that never changes, and we'll get a +1 because we kicked out that positron. So it's kind of the opposite of an electron, really. That's why it's called a positron. Now, again, you could add them up, but that really doesn't tell you the whole story, like why those numbers changed. But to check your work, making sure that everything kind of lines up on this right side with the left side. So go ahead and let's look at a positron emission example. So we're going to start with carbon 11, and it undergoes a positron decay. So carbon, we have 6 for our atomic number because it's carbon, and 11 is our new atomic mass. So we know that carbon, for positron emission, we have to have a positron come out. So we have that there. Now, remember, our atomic number has to decreased by 1 because we took a proton and made it a neutron and a positron. So that's going to give us 5 for our new atomic number. The atomic mass will not change, and which 5 is going to leave us with boron. So we have boron 11 is our new element that we have created from this nuclear decay. So remember, positron, we take a proton, make it a neutron and a positron. The positron gets kicked out, and we're left with a new isotope of boron. So go ahead and go answer questions 8 through 12. 8, 9, and 10 are questions about the positron emission. 11 and 12 are just feedback for me. Kind of something like similar to what Play Posit did, but I still want you to ask those questions, and then if you have any questions for me or you're confused by anything still, we can talk about it.